The integration by parts in this problem is awesome, and this is from the Inside Interesting Integrals book, and I do suggest you to check this book because there are a lot of fascinating integrals. And basically in my previous video I have proved this integral using digamma function. Yeah, so basically we started from the gamma function. Yeah, in my previous video the definition of gamma function is e to the power minus t to the power x minus 1 dt, and then we differentiated this function, and due to which since the t to the power x minus 1 we got ln of t, and then we evaluated gamma dash of 1. Yeah, and the answer was gamma dash of 1, which is just digamma of 1, and digamma of 1 is negative of Masonic constant. So basically for this proof you need digamma function as well. So that's why this book presents another proof without the use of digamma function, and basically by integration by parts. And the integration by parts is also really different than what we do most of the time. So let's see how do we prove this expression. Yeah, so basically first of all let us write this as integral from 0 to infinity e to the power minus x ln of x dx. Okay, so now basically through integration by parts we will try to take this integral into another form. Now, another form of the definition of Euler-Masonic constant is integral from 0 to 1 of 1 minus e to the power minus x by x dx minus integral from 1 to infinity e to the power minus x by x dx. So this manipulation is basically given by Gauss, and I have already derived this as well in my video over here. Check the link over here. Okay, so now we'll basically try to take this integral in this form. Yeah, and basically since we have to get negative of Euler-Masonic constant, we will just get plus over here, minus over here. So let us see how will we get that. So for that, first of all let us try to break this into two integrals. Integral from 0 to 1, yeah, just like the result that we have to get, and then from 1 to infinity gx. Okay, so now there are x in the denominator. We basically, sorry, not just gx, okay, to the power minus x dx over here as well. Now we have to use integration by parts. Yeah, and also taking care that ln of x is differentiated so that we get x in denominator. Yeah, since we need an x in denominator, we need to differentiate ln of x and integrate this thing. And okay, so now we are taking this as u, this as v. Yeah, but we also need a 1 minus this thing. Yeah, so that's why for this, if we are integrating e to the power minus x, for the second one we will surely use e to the power minus x, and by minus 1 is as the integral of this expression. But as the integral of b, we can also use e to the power minus x by minus 1 plus 1 as well, because this is also the integral. Yeah, and any plus c is also an integral of this expression. Yeah, that's why we will use this, because we need this expression. We need this expression in the first one. Yeah, that's why in the first one we will use the integral of b as this thing, and for the second one we will use integral as this this thing. So basically, up to this point, I never really used the integral plus c. Yeah, and this is the first time, and I was really surprised because that was completely allowed, and why did I not do it ever? Okay, now let's solve the integral. So for the first one we will have ln of x by the integral of b is e to the power minus x by minus 1 plus 1. Yeah, evaluated from 0 to 1. Yeah, and then minus, and then integral from 0 to 1, derivative of ln x is 1 by x, and this integral is minus e to the power minus x and then plus 1. Is it? Okay, that's fine. And then dx. Okay, now this is the integral of the first integral, this one. But this one also will use integration by parts, but here we won't use this special plus form. We will just use the normal. Okay, so basically we'll have 1 by x e to the power minus x going from 1 to infinity minus integral from we have 1 to infinity 1 by x e to the power minus x. Yeah, so basically we have this second part already. Yeah, okay, we have the second part already, and we just need the first part now. Yeah, okay, and I basically forgot something. Also there's minus 1 over here in denominator. Yeah, I forgot that. Also there's minus 1 over here in denominator. Okay, now after this it's not like that tricky. Like the tricky step was only this integration by parts where we had to use plus 1 as well. Now after this we will easily get it in the form. Now also over here when we have x as 1, we have ln of 1 as 0. Yeah, that's why it's 0. But when it's 0, we have over here minus 1 plus 1, which is 0, but over here we have infinity. So 0 times infinity is indeterminate. That's why we have to take limit. And even if we limit, if we use L'Hopital's rule, it will not be that hard. Let's see. If we use L'Hopital's rule, limit x tends to 0, ln of x by 1 minus e to the power minus x. Yeah. Now we have to take it to the form of infinity by infinity or 0 by 0. So that's why we will try to take the second expression in denominator. We 1 by 1 minus e to the power minus x. Yeah. So basically, I can also write this as I can also write this as this is e to the power. Okay, so e to the power x by e to the power x minus 1. Can I? Yes, I can. Now this is in the form infinity by infinity, because here also we have 1 by 0, that's infinity. Now we will use L'Hopital's rule. So we have 1 by x, and over here we have b. So basically we differentiate both numerator and denominator. Yeah, basically we will also this is equals to f dash x plus d dash x. That's why we try to differentiate them. Okay, so basically now b u dash minus u p dash by b square. Yeah. Okay, so now after this it will simplify to simpler expressions, and then it will not be that hard. Let's see how. Now after this we will have e to the power x square minus. Okay, so we will have 1 by x by, there we will have minus e to the power x by e to the power x minus 1 whole square. Yeah, now let us take it to the numerator. That's why we will have e to the power x minus 1 whole square by x times minus e to the power x. Now I can write this as e to the power x minus 1 by x. Yeah, and then we can have e to the power x minus 1 by minus e to the power x. Now this can be easily evaluated because this one is a standard limit theorem. This one is just 1 because this can also be found out using L'Hopital's rule. Yeah, this can be easily evaluated. We can just differentiate it both the numerator and denominator, and we can get 1. And for over here we have 1 minus 1 is 0, but this is just minus 1, so this is 0. Yeah, so the limit is 0. Okay, now basically this expression is 0 at both 1 and 0. Yeah, at 1 also this is 0, at 0 also this is 0. Fine. Minus, now what about this integral? Okay, so this integral. Okay, so okay, wait a second. So this integral we get positive, this integral we get negative. Okay, that's fine. Now this integral is integral from 0 to 1 minus e to the power minus x by x dx. Yeah, plus now in this integral, okay, this is done. At infinity we will have e to the power minus infinity by infinity. Yeah, but e to the power minus infinity like shrinks way faster. Yeah, and yeah, basically these are supporting each other, by the way. So this e to the power minus x will also be in the denominator, so both of them are in the denominator. 1 by infinity is just 0. and then minus. Okay, so minus, and also here is a minus sign, so that will be plus. And now, do we have e to the power minus 1? Yeah, wait a second. So now, okay, basically it's not differentiated over here. I'm sorry for that. We just differentiated over here as well, here only and not here, just like I have done here. I'm sorry for that. So this is just ln x. I'm sorry for this. Yeah. Now, yeah, okay. Now, at infinity we have infinity times 0. Yeah, but e to the power minus x dominates because this rings way faster. That's why we have 0 over here, and minus is plus, and so again e to the power minus 1 is just e to the power minus 1, and ln of 1 is 0, so that's just 0 again. I knew that it would be 0 plus 0, by the way, but like I didn't see that, so that's why I knew there was something wrong. And then minus, uh, okay, you can use minus sign to make it plus, an integral from 1 to infinity e to the power minus x by x dx. Okay, so finally it's in the form that we want. Yeah. So basically it's also kind of because we knew the result, that's why we were able to make this manipulation. Yeah. But I wonder like how would the people approach this sort of idea without the solution. That would be a pretty tough task, I would say. Now take the minus common. We have integral from 0 to 1, 1 minus e to the power minus x by x dx minus integral from 1 to infinity e to the power minus x by x dx. Okay, and we know that this is Euler-Masson constant, so minus of Euler-Masson constant. That's the proof. Hope you enjoyed the video. Yeah, though I did make some mistakes over here, but yeah, this limit was also nice. Hope you enjoyed this proof, and hope you have also checked the derivation of this formula and this diagram of one formula. Both of them are in my channel. Hope you enjoyed the video. Look forward to seeing in the upcoming videos too, and thanks to @sigma.8333 for the suggestion. Thanks for watching.